With that done, we'll now take a closer look at the other options on a vSwitch. So if we say Edit, number of ports elastic. Now this is an interesting element. It used to be that when you defined a virtual switch, one of the things you asked for was how many ports do you want by default on that virtual switch. If memory serves, I think the default was 128 virtual ports. Now, whilst you could of course increase that number, each port actually consumed a very small amount of memory. It is only very small, but for each port you add to the vSwitch, you are consuming a small amount of memory. With vSphere 7 though, it is elastic, so it will add those virtual ports to the virtual switch as they are required by the host automatically. Now the security tab, there's some very interesting options here. Now, as we saw on the port groups, we can override these settings, and I'll show you that again in just a few moments, but these are the defaults for this particular vSwitch. Promiscuous mode. Promiscuous mode allows the virtual machine to receive traffic that is intended for other virtual machines on the same virtual switch. Now it's rare that you'll turn that on, however, its main purpose is for something like an intrusion detection system or intrusion prevention system that needs to scan the traffic that is going to all of the other virtual machines. MAC address changes allows the operating system running inside the virtual machine to request a change to its MAC address. Again, you'll normally leave this on the default of reject, but you might use it with some load balancing solutions like Microsoft Windows Network Load Balancing in unicast mode, because in that mode it generates a virtual MAC address which it shares between the two virtual machines. And if you have that set to reject, it won't be able to do that because it will want to change its MAC address to the virtual MAC address that it is using for that function. And forged transmits allows the virtual machine to send traffic using MAC addresses that do not match its own MAC addresses. Again, you'll normally leave that to reject. There is one other scenario under which you might need to turn all of these to accept, which is if you're doing a lab environment within nested virtualization, which is exactly what I am doing. On my parent host, where I'm running my 4 VMs, including the 2 ESX hosts that I'm running these labs on, I've had to set all of these to accept. And the reason for that is the virtual machines inside of my virtual hosts will be using different MAC addresses to what is actually configured on the host itself, because each virtual machine has its own MAC address. They don't hide behind the host's own MAC address. So you have to change those all to accept if you are using nested virtualization within vSphere. Traffic shaping is fairly straightforward. It's unlikely you'd set this at the vSwitch level, because this will affect all of the port groups and all of the VMs that you have attached to the host. It's much more likely that you would configure these on the port groups. And then teaming and failover we've already looked at, but we'll go into these in more detail now. So load balancing, how do we split the traffic amongst the different network adapters, the physical network adapters that we have? So the default is route based on originating port. Now this uses an algorithm, so you'll remember on the properties page here we have number of ports. So this is a switch, it's a virtual switch, but it is a switch nonetheless, and it has a number of ports, and each port is numbered. So my vCentre virtual machine there might be on port 1, my Windows 10 virtual machine might be on port 2. In this case they're probably not, because they're on separate hosts. So this is a vSphere standard switch again, so this is all based on a single host. But each port has a number, and VMware uses an algorithm which produces a modulus to decide which of these NICs it should use. What that means is that each virtual port, each virtual NIC in each virtual machine will be assigned to a different physical adapter. So there's not really a lot of load balancing happening at that point on a per VM level. However, two separate VMs will be using two separate NICs. And that assignment does not happen in a sticky fashion. Okay? It will be, if one of those NICs goes down, it will simply start using one of the other NICs. It's not a fixed assignment. However, it does make that assignment at the point that the virtual machine is started. But if the virtual machine is running and one of the NICs fails, it does still fail over. Route based on IP hash. That is actually how you configure a link aggregation group. So if you're using LACP, Link Aggregation Control Protocol, on your switches, that's what you would use, route based on IP hash. If you do not have support for Link Aggregation Control Protocol or LACP on your switches, you should not enable route based IP hash. And bear in mind there will be configuration required on your switches. Route based on source MAC hash again uses an algorithm which produces a hash of the MAC address that is sending this particular traffic, and it uses the outcome of that hash to decide which network card to use. And then use explicit failover order is pretty straightforward. It will start at the top. If the first one is down or fully utilized, it will move on to the next one. Route based on source MAC hash and originating virtual port are usually actually the same thing, really, because most of the time you've got a one-to-one relationship between your virtual network adapters and the MAC addresses. However, using source MAC hash can increase CPU usage. It's only a small amount, but if you could think about it like this, each time the host is booted with originating virtual port, the host decides which physical NIC it's going to use for that VM's traffic, and then that remains until something prompts it to change, such as the failure of a physical NIC. With source MAC hash, it has to make that decision on every single frame. So it has to perform that hash of the source MAC address and decides which port every single frame that the switch sends out. So in that sense, that's why you would probably want to stick with originating virtual port, unless you do have a scenario in which you have multiple MAC addresses within a single VM. 99 times out of 100, you're just going to leave it on route based on originating virtual port, unless, as I say, you are using Link Aggregation Control Protocol on your switches to use route based on IP hash. That, by the way, is the only way to have traffic from a single VM or a single NIC within a VM to be split across multiple physical NICs. Okay, so we're going to leave that on originating virtual port for now. Link network failure detection. Now there is link status and there is beacon probing. Link status, literally, is this port up or is it down? It doesn't consider the fact that the switch's uplink to the rest of the network may be down. So you could be sending traffic through that port, not realizing that the switch has got a problem and it can't get to the wider network. Beacon probing gets around that issue. Let me show you how. Beacon probing is a feature of vSphere switches that allows vSphere to detect a connectivity issue when the NIC still has a connection to the physical switch. For example, the loss of the uplink on the physical switch. As you'll see though, it is a basic solution with a number of flaws, so for this reason, it's rare that you'll see it in use in the real world. For this example, we have a host with 4 physical NICs. Each one is connected to a separate switch. Each switch is in turn connected back to the core switches. Beacon probing is a vSphere switch feature, and remember, vSphere switches operate at layer 2. so the default gateway, router or any other IP addresses are not a factor. Beacon probing sends frames out from each physical NIC using a virtual MAC address. When the switch receives that frame, it won't recognise the MAC address, so will broadcast the frame on all ports. The other NICs will then receive that broadcast, confirming that the connectivity is good between all of the NICs. If the uplink on access switch 3 goes down, then this broadcast will not be received by NIC 3. So vSphere will ascertain from this that NIC 3 has an onward connectivity problem. Additionally, none of the other NICs will receive beacons sent by NIC 3, further confirming the issue. Beacon probing requires at least 3 NICs. If you only have 2 NICs, then when one of them has an uplink issue, then neither of them will receive beacons. So vSphere cannot tell which of the two has an issue. This isn't the only weakness. Let's look at another, more realistic example. In the previous example, each NIC was connected to a completely different physical switch. But in the real world, you'll likely have 2 NICs connected to each switch. But this is not a recommended topology for beacon probing either. Imagine access switch 2 suffers an uplink loss. NICs 1 and 2 will be receiving each other's beacons, and NICs 3 and 4 will also receive each other's beacons. So again, vSphere cannot tell where the problem actually is. Beacon probing offers no configuration options. It is on or off. It also operates at host level, agnostic of vCentre or any clustering features, so we can't even use other hosts as a tiebreak. And as this is a layer 2 feature, we cannot use the default gateway to aid in these decisions either. A more effective way to mitigate against uplink loss is to use link state tracking on your switch. This feature will shut down certain switch ports in the event that the uplink is lost. This is known by a few different names. HP call it Smart Link, Cisco call it link state tracking, but the configuration usually involves defining a group of uplinks or master ports and some access ports or slave ports that will be disabled if the uplinks are lost. For these reasons, beacon probing is rarely used. If it is enabled in your environment, I suggest reviewing your network topology against the examples I have given here. It is possible that beacon probing was enabled previously without an understanding of its limitations. Notify switches triggers the host to send updates to the physical switches, your normal physical 24, 48 port, Cisco, HP, whatever physical switches, to notify them of MAC address changes. Now this is desirable because it reduces latency on the first packet. The way physical switches work is if they don't know where to find a particular MAC address, they will flood it on all ports. They'll send it out on all ports and hope that someone finds it. The way it knows how to look for those ports, and the way it knows where that MAC address is and which is the best port to send that traffic down on, is based on where the traffic last came in from. So it knows it last saw traffic from port 3 coming in on that MAC address. And so it stores that in its table, and it knows next time it's got a packet to go to that MAC address, it sends it out on port 3. So notify switches sends a frame into the switch to let it know that this MAC address is now over here, and that prevents it unnecessarily flooding that traffic. Failback is the same as in any other system. If we fail over to another NIC because this one failed, so we're using vNIC 0 for this particular piece of traffic, and we now want to, and we failed over to vNIC 1 because vNIC 0 went down. Do we fail back automatically, or does it stay on the NIC that we failed over to? By default, that is yes.